All right, Unit 10, acid-base equilibrium. It's going to be a really quick unit, and I need you to pay attention to detail in this unit because the little things are going to add up and prepare you for the unit on buffers. Let's go ahead and look at our first slide. We need to know how to define different acids and bases. So there are just scientists out there who decided, oh, I'm going to say this is an acid, and other ones came, no, I think this is an acid. These are just definitions. There are lots of ways you can look at a situation and define it. So Arrhenius is your first set of definitions, and you do need to know what definition goes with what name. Arrhenius acids and bases are, you're looking at what's produced in the solution. An Arrhenius acid is something that produces an H+ in solution. An Arrhenius base is something that produces an OH- in solution. Simple. So when we talk about water, because water is the basis of everything we do in this unit, I'm going to kind of clear up some things and talk a little bit about where pH comes from. What you need to realize about water is if I had a water bottle, I had water in here, I don't just have H2O liquid. Okay? Water actually ionizes a little bit, not a lot. Water will ionize into H+ and OH-. Now, not very much. Otherwise, you'd be drinking a lot of ions when you're drinking water, which wouldn't be necessarily a good thing. So if I were to draw arrows, it would be very much favored in the reverse direction. So thinking about equilibrium, if I were to ask you to write an equilibrium expression for this, K would be equal to what? Products over concentration of products. Do I put the water liquid in there? No. So that's the equilibrium expression for the ionization of water. Because water is water and it's special, they put a little subscript there called Kw. Okay? Now, what is the value of Kw? You actually did this in first year, but they didn't relate it to equilibrium like this. You actually memorized a number. Does anybody remember it? 1 times, yep, 10 to the negative 14th, exactly. That number is just the K for water. We did K's all unit. I gave you the K for that. You know, you guys calculated K for that lab you did. It's just a K. So if I were to say, okay, now that you know the Kw, what would be the concentration of H+ and OH- if in water when it's neutral? What would be those concentrations in neutral water? Guys, math. What? No. What is Kw? Nope. You guys don't know your log rules? Really? I think I need to go talk to your math teachers. Yes, 1e-7. Do y'all see where I'm getting this? You're looking at me like you've never seen this before in your life. If this is 1 times 10 to the negative 14th, and I said water is neutral, what does that mean? What does neutral water mean? These are the same concentrations. Acid and base is the same. So this would be 1 times 10 to the negative 7, and this would be 1 times 10. Wow, I'm really scared. You guys scared me now. I thought I needed a drink earlier. Now I really need a drink. All right. What? You try teaching 32 high schoolers. See how much drinking you want to do. And just for the record, people out there, I do not drink, and I'm not an alcoholic, even though I sometimes wish I were. This is how these are how teachers get fired. Watch me get called in for this video. Anyway, another way you can write the ionization equation is through the Lowry Bronstead definition, which we'll talk about in a second. But basically, it's moving an H+ from one species to the other. So if this species donates a proton to that, we get H3O+ and OH-. I need you to know that H3O+ is the exact same as H+ in the acid-base world. except this does have a name. Does anybody remember it? Not hydroxide. Oh my God. Hydronium, thank you. Hydronium, which is the same as H+, okay? Don't think it's any different. And again, if I were to write the expression here, same as the expression there, we use W because it's water, and the value of that is 1. Oh, is that where you got 1e negative 14? You guys are sneaky. I thought you actually memorized it. Boo. I was all impressed, and you guys just yelled it out. I am such a fool. Oh, my God. Okay, so let's move on. So there was a man. He was a Danish beer maker, and his last name was Sorensen. Does anybody want to guess his first name? Did you know that, or you just... It is. It's Soren Sorensen. I don't know why his parents would do that to him. So Soren Sorensen discovered, or not, he basically created the pH scale because he was using numbers for concentration of acidity and basicity so much in his work, it got to be tedious writing these numbers over and over and over again. So it was basically a shortcut way to make the numbers a little bit easier. So he came up with the whole concept of pH or POH, where P is the old-fashioned way of saying negative log. Where the pH scale came from was this whole water deal. If I were to take the negative log of this, what do I get? Don't put it in your, do you really have to put it in your calculator? I've got to talk to your math teachers. Log base 10, guys, 14. I know you said it, but you're the only one who said it. He got 14. What is that number? How does that relate? Have you heard 14 before? That's exactly what the pH scale goes to, right? Okay, so that's where the pH scale came from. This came first. Then came the pH scale. So we say neutral water has a pH of 7. Oh, look. Negative log of that is 7. Okay, so you see how this is all coming together. That's where Soren Sorensen got his stuff. So I need you guys to know these definitions and formulas like the back of your hand. pH is a negative log. Again, just remember P is negative log. Knowing that, you know that it's a negative log of H. POH is the negative log of the OH minus concentration, and the concentrations have to be in moles per liter. They're complementary scales, so when you add them up, you get the total of 14. You've got to know that as well. In addition, don't forget that KW equation, because you can go between all of these in different ways. Some of them are shorter than others, but a lot of people tend to avoid that one for some reason when it's actually a shortcut in some cases. Okay? pH range refers to just that, pH. So we have said that, oh, if it's a pH less than 7, it's acidic. If it's a pH greater than 7, it's basic. We could very well use the POH scale, but just know that it would be reverse on the POH scale. Why Sorensen liked H plus over OH minus? I don't know. He looked at H pluses. So be familiar with that. And you saw it a little bit yesterday in your Chatelier's lab where did you get more basic or more acidic when you did your little stuff? More acidic. And I figured out why some of yours disappeared, because there wasn't enough indicator in there. That's what it was, rather than changing color. So everyone, it went from orange to pink. That's what it was supposed to do. Okay. So what we're going to do here, in order to use pH and figure things out, I need you guys to know how to write dissociation equations. What does it mean to dissociate? To break apart into what? Ions. So we're going to dissociate or ionize. In order to do this successfully, we need to do a quick review on strong and weak acids and bases. What's the difference between a strong acid and a weak acid? Strong acids ionize how, Miles? Not more, but 100%. Every single HCl is going to make an H plus and a Cl minus in solution. If it's weak, some of it will, some of it won't, and it's going to go back and forth. What is back and forth? What is that again? Equilibrium. So if we have a weak acid, we write our dissociation equations with a double-headed arrow. If we have a strong acid, we write our dissociation equations with a single-headed arrow. What were our strong binary acids? Who remembers? I bring clay. Oh my God, you learned something. So excited. All right, I bring clay. And then what about the ternary acids? What was that rule of thumb? 2 or more what? O's then H's. Okay. The next thing then there's one type of acid that's always weak. Who remembers? No, that's base. Close. Carbon-containing. No, that's a base. Carbon-containing acids. Any acid that has a carbon in it are weak. Okay, let's talk about the bases then. And I'll go back up and do the problems. What are our strong bases? They're all our hydroxides, which are what? Group 1, and there's another couple hydroxides that are strong. Yeah, I heard. Right. SR, perfect. SR and BA, the bottom two of group 2 and group 1. Those are my strong bases. Now I heard a ton of you say that. What's the consummate weak base that you need to know by heart? Ammonia. This is a weak base. So if you know this information, you're going to be fine when it comes to doing stuff like this. So let's go back up. All right. For aqueous solutions of the following substances, write the dissociation reaction. So, and then we're going to say if it's Arrhenius, acid, or base. So here, all we're going to do is dissociate. We're going to first figure out what kind of acid or base so we know what arrow to put. HF, strong or weak? Weak. So it doesn't dissociate 100%, so we're going to put a double-headed arrow. For the few that do dissociate, what are we going to do with ions? What are we writing? Correct. So this is where detail is important. The type of arrow is important, as well as the charges on those ions. Students start to miss a lot of points here for being careless, okay? Yeah, I mean, no, I'm not going to. The question was, do you have to write aqueous, aqueous? If I ask for a formal, not ionic, I'll say include states, then you would, but no. All right, so this we decided was a weak acid. What's this? Weak acid, why? Carbon containing. Since it's weak, double-headed arrow, what ions do we dissociate to? Good. Okay. Barium hydroxide. Strong base. So this is going to be a single-headed arrow. What are we going to make? Plus. Good. Lithium hydroxide. Oh, and I'll got to go back in a second. What do we make? So go back up. I forgot to answer this. If it's an Arrhenius acid or base, this produces an H+, so this is an acid. This produces an H+, so this is OH, OH. Okay, simple. Now, water. Water, we know, doesn't do anything strong, so we know it's going to be in equilibrium with what two ions? Arrhenius, acid, or base? Both. I'll give you both. It's neutral, but according to the Arrhenius definition, it does both, right? It produces H+. So anyone know, remember the term for this? Let's see, I'm going to go slow. Not amphibian. Amphocyte? Nope. You guys are horrible. Forget it. Thank you. Amphoteric. I have a feeling y'all learned that. After hearing it, you don't remember it? I got to talk to your Chem 1 teachers now. You would love to see us fight, wouldn't y'all? Miss Rozier and I? Hey, I'm a ninja, just FYI. You guys are being mean and nasty now. All right, this last one, I want you to put a little star by because it's actually pretty important. And that's because, how does this acid look different than any of the other ones we did? H2, correct. There are two H's. We call this not proteric, just diprotic. Diprotic, meaning two H's. Diprotic. Sometimes people say polyprotic, meaning more than one. What would a 1H acid be called? No, monoprotic. The reason we don't care in bases because bases ionize just like normal salts do. Acids are strange in that they only ionize stepwise. So meaning only one H comes off at a time. We're going to do more with this later, but since this is a weak acid, it's an equilibrium because it has a C, only one H comes off at a time. Please pay attention to acids with that. And so we make H plus, and what's left over? HCO3 minus, okay? And then later on, if the conditions are right, this HCO3 minus will also, not very little, it gets harder and harder to do. So let's talk about the K's with that. If it gets harder and harder to do, the forward reaction happens less and less. So what would happen to the K value from here to here? The K gets much smaller. Remember, products over reactants, we have less products the more H's we take off, so the K value, we call it Ka for acids, is going to decrease as you take off more and more and more hydrogens. We are going to cover that, so don't freak out yet. I'll go into much more detail later. All right, are we good with dissociation reactions? Check. All right, now we need to do some calculations. You have to know how to do these keystrokes in your calculator. I'm only going to do two examples with you. I'm going to do A and B. I'm not doing any of the others because you guys need to do your homework and practice this stuff. Okay? It's not hard. It just takes practice. This is Chem 1 stuff. So we're going to calculate pH and pOH for both of these. The order you do it doesn't matter. You want to go in the order that gives you the easiest route. So if I have H plus, what do you think is the first thing I should calculate? pH by doing what? Negative log of H plus will give me my pH. So go ahead and give me a number for that. Give me a bunch of sig figs. Any day. Okay, say again. Is that right? That sounds better because it's a, 2.39. All right, so what I do want to talk about is sig figs. pH has weird sig figs. The only part of a pH that's significant and it counts as sig figs are the decimal places. So right now, this is a 4 sig fig answer. What was the number of sig figs in our concentration? Normal sig figs. 2. So we need a 2 sig fig pH, which would be 2 decimal places. So the answer is 2.85. They do look for this on the AP. So the only part of a pH that's significant is the decimal places. That has to do with the fact that this is a log-based thing, and the 2 refers to, like, I forget the abscissa or mantissa or whatever the math term is. So we only look at the decimal places. Okay, let's talk about finding this POH. There's a couple ways we can do it. What's the easy way? Subtract from 14.00, and what do we get? 11.15? 11.15. That's the easy way. There is another way to do it, though, and I want just to talk about it. You don't have to do it that way, but you need alternatives in life. Life lesson from Demo. It's all about alternatives. Plan B. So if I had H+, what would be another way to find pH? Okay, well, what could I get from H+? Directly. Concentration of what? OH-, exactly. I could use this equation using the Kw value, solve for the OH-, and then take the negative log of the OH- to get POH. It's more steps, but you need to know that that's a possibility, okay? Don't forget about this equation. It's a good equation. All right, let's do this one. If I've got OH concentration, what makes sense for me to find first? POH. So negative log of 2.08. Give it to me with the correct sig figs this time. Quickly, guys, we're running out of time. 6 point, good. 682, 3 sig figs. So 14 minus that is 7.318. Y'all good? Is this solution based on pH acidic or basic? Above 7. What about the previous one? Oh, oof. Look at your pH scale, not your pOH scale. And if it's above 7, it's basic. If it's below 7, it's acidic. All right. Now we have to go backwards really quick. When we go backwards, we need to do the inverse log. Really quick, guys. Oh my God, I'm so scared we're going to run out of time. pH is equal to the negative log of H+. In this case, we're solving for what's in there. So if we were to isolate this, the negative would go on the other side, right? I'd have to do that first to isolate this. Now what do I do to get rid of the log? Right, 10 to the. So the keystroke is 10 to the negative pH value, or 10 to the negative POH value to actually find those concentrations. So you can't forget the negative. So really quick, with 2 sig figs, give me the H+ concentration of this guy. Quick, quick. What now? I heard the 3.9 moles per liter because it's a concentration. Now, how would I find OH- from this directly? Kw. So 1e negative 17 divided by 3.9 e negative 8, 1e negative 14, excuse me, divided by 3.9 e negative 8 is 2 sig figs. Times 10 to the negative 7 moles per liter. Got it? Do I have to do another one? Practice this at home. You got to get those keystrokes right. Okay? I need to move on because we've got like 5 minutes left to do conjugates. All right, Bronstead-Lowry is the most important definition of acids and bases. We call Bronstead-Lowry acids proton donors and bases proton acceptors. Why do I say proton? Hydrogen plus. What does hydrogen normally have, not as a plus? It has a proton and an electron, right? When it's a plus, electron goes, so this is literally just a proton. So this we know is an acid. This then would be the base. This would be the proton donor, making H3O plus and Cl minus. You need to know how to identify conjugate acid-base pairs. The conjugate acid-base pair only differ by 1H plus. This is an acid. That makes this the conjugate base. This is the base. That makes this its conjugate acid. The conjugate acids and bases are all on the product side. Why is this a conjugate base? Well, if I were to go this way, you see how this is a proton acceptor in the reverse direction? That would make it a base. I want to skip 2 slides. I'll come back if I can. We've already done this. I'll come back to these if I can, but this is the most important page right here. For the following compounds, write the reaction with water and indicate acids, bases, and conjugates. We already did this one. This was the example from the previous page. Let's do this one. We're going to add it to water. What do we know about NH3? It's a weak base, so we're going to have double-headed arrows. According to Lowry, Bronstead, bases do what? Proton acceptors. So that makes this NH4 plus, leaving behind OH minus. That, my friends, is why ammonia is a base. This. Okay? Because it makes OH in water. So this is then the base. This is the acid. What is NH4 plus? Conjugate acid, and this is conjugate base. All right? HCN plus water. HCN is a what? Weak acid, so double-headed arrow. What do we make? Acid is a proton donor, so we make CN minus and H3O plus. That makes this the acid, this the base, this the conjugate base, and this the conjugate acid. I'll skip D because of time. What I really want to focus on is this weird one. I don't want you to freak out anytime you see something like this. This is something called a nitrogenous base. It is a weak base. Nitrogen will kind of be the center of that base, and it's got 4 spots it can have stuff on, okay? It's got 2 H's, and then it's got this whole group, this ethyl group. So it has 1 spot where it can fit something, okay? So everything is just tacked on or taken off of the end. Don't break apart groups. Only tack on stuff to the end. These are always weak. So if we add water to this, this is our base, nitrogenous base. If we add water, the base is a proton acceptor. So we're going to get CH3, CH2, leave that alone, and just add the H to the back side. What does it do to the charge? Plus, and that makes this what? OH. Again, that's why it's a base. Look what it makes. So this is the base, this is the acid, this is the conjugate acid, this is the conjugate base. Okay, I'm going to keep going, so when the bell rings, I'm going to keep talking. You guys can get up and leave just because I want to finish the video. So for each of the following acids, write the formula for the conjugate base. Don't freak out. What do acids do? Donate a proton. So for this to be an acid, it has to donate a proton. When it donates a proton, what does it make? H. We're only writing the formula of the conjugate. H, PO4 minus 2. When this donates, what does it make? ClO2 minus. When this donates, what does it make? NH3. Good. Let's go to the next one. For the following bases, write the formula. What do bases do? Accept. So when OH minus accepts, we get H2O. When Cl minus accepts, we get HCl. When water accepts, we get. So that's the conjugate. So remember, conjugates only differ by 1 H. If they're acids, they'll take them in. If they're bases, if they're acids, they'll donate them. If they're bases, they will take them in. Okay, let's practice this one. This is going to be a base, so it's going to accept. What are we going to make? No. Remember what I said? Chunk it on the end. Just chunk it on the end. Here, CH3, CH2, NH3+. Just chunk it on the end. Okay? It's taking up one of the 4 spots. On the previous slide, this is a trick one. That is not going to donate. Do you see how that's OH minus is like the strongest base in the universe. It's never going to act as an acid. It would have to donate. And if it does, an OH minus would never want to become an O minus 2. It just doesn't happen. So this is a trick. All right? How would this one become a base. It's an acid, so it would donate. What did we make? OH minus. This one, what would we make? Donate. NH2. Good. Oh, whew, we finished. That was fast. So we're going to start pHs. I was originally supposed to do this slide with you guys and do pH of strong. For now, to get a pH, just take the negative log of the concentration of acids to get the pH of an acid. For a base, just take the negative log of the concentration of the base to get its pH. Okay? Well, it's actually, if you take the negative log of this, that gives you POH. I'll explain why we do that on Monday when we'll do pH of strong and weak acids and bases.